Okay, so what I want to round off with sort of our understanding of our shape functions and where we put the nodes, how we do the meshing essentially, is to talk about what happens if our mid-side node is not in the middle of a three-noded element. So I've got a quadratic element, x1, x2, x3 are the nodes that I'm putting down. I'm choosing where I put them, but I now choose to put x3 such that it's not in the middle of x1 and x2. This is what I'm choosing now. What is the implication of that? And what I want to show you is that is how we get mesh distortion. And later on we'll talk about mesh distortion again, but this is essentially the consequence of a distorted mesh in 1D. And so when we do this, I can then, first off, we can use the isoperimetric formulation to write that relation between x and psi. This is what we get. And if x3 is not in the middle, okay, and we just keep on working out the derivative of x with psi, with x3 now as its own value that we have, we see essentially that the relationship between x and the derivative, the x d psi's relationship, is linear. You see there's a linear term, there's a linear term, there's a linear term, there's a, it's not constant anymore. That is important to understand. Okay. And so if that is the case, what is the implication of this? Okay, so we can see it's a polynomial, a linear polynomial. Okay, that's bottom line. All of these x1s, x2s, x3s are known, and they multiply them all, but we'll get something that's a linear relationship. Okay. Remember when x3 was in the middle, it was such that things cancelled out, that the derivative, the x psi was a constant, but now it's not, it's just a linear term. The implication is when you look at the stiffness matrix, remember the stiffness matrix had this b, which was d psi dx multiplied by the derivative of n with psi. These n's with psi's derivatives were sort of linear terms that we had. These were polynomials that we had. Okay, that is, but this d psi dx was the 1 over this x d psi. So d psi dx now becomes 1 over some linear polynomial. So what I have is these n's are linear polynomials divided by a linear polynomial, and I've got two of there's twice that I multiply by a linear 1 over a linear polynomial, because there's a b transpose and a b. And this is just when we talk about a single b, that there's a d psi. So there's a polynomial divided by polynomial. So here, this is polynomial divided by polynomial. This is another polynomial, again, polynomial divided by polynomial. That's what we have there. Then we have the integration constant that we had. Okay, the relating d psi to dx. That was the x d psi, which is just this dx d psi that we had here. So what we have is we have 1 over d psi dx times another d psi dx multiplied in the end by the x d psi. So one of those dx d psi's will cancel with one of these psi dx's, but then I'll still be left with one of the d psi dx's. So I'll end up with something that is a polynomial divided by polynomial, because here is a 1 d psi dx, there's a d psi dx. One of this d psi dx will cancel with this dx d psi. Okay, they'll be become a unit, but then I'll still be left with 1 d psi dx. So I'll end up with polynomials divided by polynomial. And when that's the case, my Gauss quadrature is inexact. Okay, I'm not able to do an exact Gauss quadrature. So what we talk about in finite elements is when I use a the Gauss quadratures, when I the number of Gauss quadratures when I choose, if I were to choose them for an element that was not distorted, so if that mid-side was in the middle, how many Gauss points would exactly integrate it? We call that full integration. Okay, so that is what full integration would like, because the fact of the matter is, as soon as I have a distorted element, I end up with infinite number of polynomials required to integrate that exactly, typically. And so, in general, we can't talk about how many Gauss points we need to exactly integrate a stiffness matrix. What we can ask is, how many Gauss points do we need if we make the assumption that this element was undistorted, and that's what we call full integration. Okay, so please take note, when I talk about full integration, I'm referring to integrate an element when we make the assumption that the element is undistorted, so that this stiffness integrand is just a polynomial. This whole thing is just a polynomial. But in general, if the element of the mesh is distorted, we end up with a polynomial divided by a polynomial, and we'll always make some Gauss quadrature mistake. But full integration will be number of points if this was an undistorted element, to make sure that that integral is at least exact. Okay, so that concludes sort of a little bit of insight about what the mesh distortion's role is. So when we have a distorted mesh, we're making integration errors. Okay, we're not integrating exactly, we're making some mistakes with our integrations. Okay, that concludes